Hello, everyone. So today I'll be presenting on the investigation of mechanical splices for titanium alloy bars. This is the research carried out at Idaho State University. Okay. So yeah, today I'll be talking about some of the objectives, and I'll also be presenting some of the literatures that are out there, and then present you the experimental program, which is basically the tension test that was carried out at Idaho State, and also provide you some of the discussions and conclusions. So like I already mentioned, I'll review some of the literatures that are available on the titanium alloy bars, both the research and current use side of it, and provide you the experimental results. So first, titanium alloy bars, the widely used in civil infrastructures, civil engineering industry, the widely used grade of titanium is grade 5, which is an alloy of titanium, aluminum, and vanadium. Also Ti6L4V. This is the one that we've used. And then some of the advantages that this type of titanium offer is the great corrosion resistance and high strength to weight ratio, flexibility, ductility, and then less modulus of elasticity compared to the normal steel. And then the most disadvantages it is an expensive material. So this is one of the research that was carried out at Oregon State University. What they did was, so mostly they have used titanium alloy bars for the retrofitting. So this is one of the research carried out at Oregon State University. And then what they did was they took the square column and then they used titanium longitudinal reinforcing is titanium alloy bars, and those spirals are also titanium alloy bars, and they were trying to match, or they're trying to obtain the upgraded capacity of the column or restore the capacity of the column. And then actually they obtained the improved seismic performance using the titanium alloy bars retrofit. And then some of the advantages that they obtained was high strength with well-defined material properties and improved ductility. And another definite thing is they obtained the economic retrofit solution compared to FRP retrofit and other traditional retrofit solutions. So the first plot there, you can see the stress strain plot. This is one of the research that was carried out at Idaho State University. So there in the red, you see the 150 KSI steel, the red dotted, and then black is the titanium alloy bars. So there, the red dotted is actually the 150 KSI steel to match apple versus apple, I would say. And then the first part of the figure that you can see is the NSM technology that is used by the Oregon Department of Transportation. And then the middle part is used in the San Jacinto River in Texas DOT. They have used to retrofit the bridges using the titanium alloy bars. And then now that people have seen the potential of titanium alloy bars, so ASHTO in 2020, they published their first edition of the guide for design and construction for the near surface mount technology using the titanium alloy bars. So with this, we looked into so first, we cannot use titanium everywhere because it's expensive. So we decided to look for the splicing options for titanium alloy bars to see so that we can just apply it wherever needed, like in plastic adhesives. So there are 3 different couplers that we looked around. The first one, as you can see, is which uses the shear screw to splice the bar. You just insert the bar from 2 ends, and then there is the positive center in the center of those couplers, and then you just tighten those shear screws or twist off those screws. And then second coupler is the coupler B. So what they do is, again, you insert the bar from 2 ends and then you zap it, or you grip it. And then this kind of coupler uses cold swag steel sleeves. And then, like I mentioned, they are installed in situ with overlapping bites. and then they are gripped using the portable presses. And then the third one, so this type of coupler was designed specially for high strength bar, and what it does is, so it also uses the cold sway steel sleeve, and it is comparatively thicker than other two couplers. And then there are both male and female ends where you screw them, and then to maintain the full cross section area of the coupler. So for the experimental part, this is basically the ASTM A1034. This is the typical tensile test setup for the bars. And then, so testing matrix, we basically considered mostly number 5 and number 6 bars for our to make up our specimens. And then we just use one number 14 bar to see if it breaks or not, just to see if it breaks or not. But mostly there are number 5 and number 6 rebars used. A is the first coupler A, B is for the coupler B, and then C is for the coupler C again. So with the coupler A, which is using the shear screw one, so it was not able to break the bar basically. So because it had the pullout failure, as you can see, the inside in the picture, they're having the pullout failure of the screw instead of failing the bar. However, there was also, you can notice from the change in diameter and change in length, it's very less change in diameter and change in the length of the bar. And this is the stress versus position plot for all 3 different bars. So not able to push it to break the bar. And then this is for the results for the coupler B. Even coupler B was not able to fail the bar, but it failed the coupler instead, which is not the failure that we were expecting. But the good thing was it was able to, this type of coupler was able to successfully grip the bar. And even here, the change in diameter is pretty low. And then this is the stress versus position plot. And then this little kink that you see is the slip of the bar. And then this is for the coupler C. So like I said, coupler C also uses the pressing thing. So that is why it was able to successfully grip the bar. And then this is comparatively thicker too. So basically we did the 6 specimens testing on this particular coupler. So all 6 specimens except specimen 2 or C2 had the bar break failure away from the splice region, and then C2 had the thread strip failure. So 1 out of 6 had that kind of failure. So we thought that is not a very big issue. And then, so like I mentioned before, failure is away from the splice area. And then, so that thread strip failure also indicates that test was pushed the coupler material near to its limit. And then all other had the bar break failure, sorry. And then, so from the experiment, we thought that the coupler C is the appropriate and acceptable material for splicing the pseudo-threaded titanium alloy bars. And so the AASHTO requires to have the specimens to achieve at least greater than 125% of yield strength, but we only achieved 120%. But we thought this would be acceptable because normal steel that is used to make the coupler goes to strain hardening. And titanium alloy bars and steel both have different strain hardening. And also titanium alloy bars do not carry large overstrength factor compared to normal or high strength rebars. And also titanium alloy bars have an elastically perfectly plastic type of behavior under tensile loads. And overstrength factor is generally about 1.1 compared to 1.5 or similar. So this is the bar fracture failure that occurred on the coupler C that you can see, which is away from the spliced region. And then the last figure that you can see the strip failure on the second specimen. And yes, this is the stress versus position plot for this one is for the number 5 bars, and then the other one plot is for the number 6 specimens on top of each other. So in conclusion, so what we can conclude is to keep the quantity of titanium alloy bars limited because of definitely the higher cost. So tensile test on spliced titanium alloy bars were carried out to identify the suitability of these different splicing systems. And then coupler C, which uses cold phase steel sleeve and is thicker, produced by producer X, seemed to be an appropriate mechanical coupler for splicing the pseudo-threaded titanium alloy bars, because the testing was successful in pushing the failure plane away from the spliced region. And also the result from the testing showed that it has really good potential in the civil infrastructures industry, but definitely there are a lot of research, and there are a lot of research need to be carried out to be to practically use this in application. And so I would definitely like to thank some of these Perryman Company, Bar Splice, and Perryman Technology for supporting and helping us on the research. And also definitely I'd like to thank my advisor for giving me this opportunity. And thank you so much.